Okay, I want you to look at your phone for a second, or your laptop, whatever you're listening to this on.
Mm-hmm.
You see a screen, buttons, maybe a camera lens.
Mm-hmm.
But if you could strip away all the glass and aluminum down to that green circuit board inside,
Mm.
what do you think you're actually looking at?
Well, most people would just say they're looking at hardware, wires, silicon chips, resistors, electricity moving from point A to B.
Right. And that's exactly what I thought too. But after spending the last few days with this stack of research on analog filters, I'm realizing that view is, well, it's pretty superficial.
I think so too.
It's like looking at a book and only seeing the ink in the paper. The whole premise of this deep dive is actually kind of radical. These circuits aren't just plumbing for electricity.
No, not at all. They are physical machines designed to perform algebra.
That is the perfect way to frame it.
Yeah.
Dictating electron behavior with math.
Yeah.
And today, we're going to trace exactly how we got so good at doing that. We're going on a bit of a journey from the heavy golden standard of old school passive components through the active revolution, and then finally to how we basically simulate physics on tiny silicon chips today.
It's a fascinating evolution because it's not just about making things smaller, it's really about control. So we're going to look at some of the math, a few famous circuit topologies like the silent key, and this really elegant concept called the leapfrog filter.
And we should be clear, this isn't just theory.
Hmm.
If these filters don't work, your Wi-Fi crashes, your Bluetooth cuts out.
Your medical equipment gives you the wrong heart rate, the stakes are very real.
So before we get to the complex stuff, we have to start with the fundamental link. The sources call it the transfer function, or
Algebra is the bridge. It is the single most important concept here. I mean, imagine a canyon. On one side, you have the physical world capacitors, resistors, voltage, things you can touch.
Huh?
On the other side, you have the mathematical domain equations, poles, zeros. The transfer function, neuros, is the contract that links them. It says, if I put the signal in, the math guarantees that signal must come out.
Okay, but let's decode the slow line dialers, because usually we think about signals in time,
Right.
a song playing second by second. But the research really emphasizes this Laplace domain. Why do we need to leave time? Why make it so complicated?
Because the time domain is messy. I mean, if you try to calculate how a complex circuit behaves second by second with differential equations, it's just a nightmare.
The math gets crazy.
Incredibly dense. But the Laplace transform lets us step into the ZO domain. And in this world, SOTA represents complex frequency. Mathematically, it's demega. It basically turns calculus problems into algebra problems.
Ah, so it's a shortcut. And this actually changes what a component is, right? I mean, physically, a capacitor is just two metal plates with a gap. It stores charge.
Right.
But in the SOL domain, the notes say it becomes a frequency-dependent impedance.
Exactly. In the Laplace world, a capacitor isn't a bucket. It's a gatekeeper. Its impedance, its resistance to flow, is defined as 1 Luller.
Okay, let's pause on that math. 1 Cephas through an Aladas. I wanted to make sure I get this. C to dollars is just the capacitance size, and C is the frequency. So if the frequency gets really, really high, then C is a huge number.
Right, follow that logic.
And 1 divided by a huge number is basically 0.
Precisely. At high frequencies, the capacitor's impedance just vanishes. It becomes a short circuit, an open door.
So if you put that capacitor connected to the ground, any high-frequency noise sees that open door to the ground and just dumps right out.
It effectively commits suicide before it can get to the output.
That's a great way to put it.
And that's exactly how a low-pass filter works. The high-frequency stuff gets shorted, and the low-frequency stuff sees the capacitor as a wall and just flows on to the output.
And the reverse works for blocking DC voltage.
Yep. DC is 0 frequency, so 0 is 0. 1 divided by 0 is infinity. The capacitor becomes an infinitely high wall. Nothing gets through.
We're literally building a physical machine that solves that equation in real time. That makes sense.
Yeah.
But here's the problem, and the sources were pretty blunt about this. These simple passive networks, just resistors and capacitors, they're kind of terrible for modern stuff.
They have some very severe limitations. The first one is obvious. They are lossy.
Lossy meaning the signal gets quieter.
Always. A passive filter can never, ever boost a signal. It can only carve away at it. The resistors burn energy as heat, so your output is always weaker than your input.
And if you chain a few together, you're left with nothing.
Exactly. But the bigger problem, the one the research says keeps engineers up at night, is loading effects.
This sounded like a plumbing problem to me.
That's actually not a bad analogy. It's a huge headache. So imagine you design a perfect passive filter on your workbench. Cuts off exactly at 1 kilohertz. Perfect.
Yeah.
Then you connect it to a speaker or another amplifier stage.
That changes the math.
Completely. That new component has its own impedance. It draws current. It effectively changes the resistor values in your original design. You've changed the variables in your equation just by plugging something in.
That sounds incredibly frustrating. So you can't isolate the stages. Every time you add a link to the chain, you break the previous link.
Which makes complex design basically impossible. You can't just build 5 blocks and snap them together like Lego.
You need isolation. Which leads us to the active revolution. This is where the operational amplifier, the op-amp, comes into the story.
The superhero of analog electronics. The op-amp changes the whole game because it turns a passive RC network into an active RC network, and it brings 2 superpowers, buffering and gain.
Buffering solves that loading problem, right?
Yes. Think of an op-amp as an interpreter. It listens to the filter with effectively infinite impedance, so it doesn't draw any current, it doesn't load the filter at all.
I see.
But then it turns around and shouts the message to the next stage with basically 0 impedance.
So it creates a wall, the filter doesn't know what's connected, and the output doesn't mess with the filter.
Exactly. Isolation. We can finally treat circuit blocks like Legos. And then there's the second superpower, gain. We'll call it H$R.
Because the op-amp is connected to a power supply, it can inject energy.
Right. We aren't limited to a max volume of 1 anymore. We can make the output 10 times louder than the input if we want.
Okay, so we have power and we have isolation. This unlocks the ability to build much more complex architectures. And the first big one in the text is the Sallen-Key topology.
Ah, the Sallen-Key. It's legendary. I mean, if you open up almost any piece of audio gear from the late 20th century, you will probably find one. It's a very clever way to use just one op-amp to create a second-order filter.
Pick-Garter, meaning it has 2 poles.
Right. So a first-order filter rolls off pretty gently. A second-order filter rolls off twice as fast. It's much more efficient at killing noise. But the Sallen-Key is famous for another reason. It's deceptively simple, but it has a trap.
The danger zone. The notes talk about a stability criteria.
Oh, yeah. This is where physics bites back. In a Sallen-Key low-pass filter, you set the gain with 2 resistors. Let's just call the gain dollars.
Okay.
Now, you might think, I want tons of gain. Let's crank it up. Make it loud.
Why not? Free energy, right?
Not exactly. The math of the transfer function dictates the dollars must be less than 3.
What happens if the lollers hits 3?
The denominator of your transfer function hits 0. Mathematically, the result is infinite. Physically, your circuit stops being a filter.
And it starts to oscillate.
It starts to scream. You build a filter to clean up a signal, but because you pushed the gain just a tiny bit too high, you turned it into a tone generator. It becomes unstable.
Wow. That's a pretty tense balancing act.
Yeah.
But the design process they outlined in the source is very structured. It's almost like a recipe to avoid that exact disaster.
It is. And the order of ingredients really matters. Step 1. You always select your capacitor first.
Why start with the capacitor? I would have thought you'd...
Pretty much. So you pick a standard capacitor, usually something over 100 picofarads, to avoid what are called parasitic ghosts.
Parasitic ghosts.
Tiny stray capacitances just on the circuit board itself. If your main capacitor is too small, the board starts to interfere with the math.
So go big enough to drown it out.
Right. Then step 2, you calculate the resistor. And step 3 is setting that gain dollars.
And this is where the art comes in. That gain value determines the flavor of the filter. If you set dollars to exactly 1.586, you get a Butterworth.
Which is the vanilla flavor. It's maximally flat. It's smooth, no bumps in the passband. But sometimes smooth just isn't good enough.
Right. This brings us to the next section, the need for speed. Because sometimes you have a signal you want at, say, 1 kilohertz and noise you need to kill at 1.2 kilohertz. They're right next to each other.
A smooth hill isn't going to separate them.
You need a cliff.
Exactly. You need a fast transition. And to get that, we have to abandon the nice, smooth Butterworth and bring in the Chebyshev approximation.
The Chebyshev. It sounds aggressive.
It's the sports car filters. It handles corners incredibly well. It dives down into the stop band much, much faster than a Butterworth.
But there's a trade-off. There's always a trade-off.
Oh.
What's the price we pay for that steep cliff?
The price is ripple.
Ripple. What does that look like?
Okay, imagine a table. A Butterworth response is a perfectly flat tabletop. A Chebyshev tabletop is warped. It has waves in it. In the passband, the frequencies you actually want to hear, the volume isn't perfectly consistent. It wobbles up and down a little bit.
So you're accepting a little bit of distortion. Some frequencies are a bit louder, some a bit quieter, in exchange for that rapid descent into silence for the noise.
Precisely. You sacrifice linearity for selectivity. And if you're filtering a heartbeat monitor, maybe you don't care if the volume wobbles by 1%, as long as you absolutely kill that 60 hertz power line hum.
Now, the notes say that if we need a really high-performance filter, say a fourth-order Chebyshev, we can't just build it all in one go. We have to use cascading.
Right. Building a complex fourth-order transfer function in one giant circuit is a sensitivity nightmare. If one component is off by just 1%, the whole thing falls apart. So we use a divide and conquer strategy. We build two separate second-order stages and chain them.
But this part fascinated me. The stages aren't identical. They have different personalities.
Yes, this is the peaking and smoothing concept. To get that sharp Chebyshev corner, one stage has to be the aggressive one. It has a high Q factor, maybe 3.5.
And it actually boosts the signal right before the cutoff. It creates a spike.
It creates a spike, and you'd think, that's not what I want, but that's why the second stage is the lazy one.
Yeah.
It has a low Q factor, like 0.7. It starts rolling off early, it droops.
So you have one stage that spikes up and another that droops down.
And when you multiply them together, because cascading is multiplication in the Steidl domain, the spike fills in the droop. And the result is that characteristic Chebyshev shape, flat-ish with ripples, then a sheer drop.
It's like a good cop-ad-cop routine. You need both to get the job done.
That is actually a great analogy. The math works out so they cancel each other's flaws and combine their strengths.
So we've got these active circuits. They're small, powerful. They use op-amps. We've mastered the math. But then the source material takes this weird turn back in time. It starts talking about the ghost in the machine, the passive LC ladder.
Ah, the LC ladder. This is the heavy metal era of electronics. Before op-amps, if you wanted a pro-grade filter for like a transatlantic telephone line, you used inductors, L, and capacitors.
Yeah.
Massive racks of them.
And the source calls this the golden standard, which confused me. We just spent all this time talking about how great active filters are. Why look back at these big, clunky ladders with such reverence?
One word. Robustness.
Sure.
Pure and simple. These LC ladders were doubly terminated. They had resistance at the source and the load. And because of the physics of how they move energy, they were incredibly insensitive to component drift.
Define drift for us.
Well, real-world components aren't perfect. A capacitor changes value when it gets hot. A resistor ages. In a Sallen-Key filter, if your resistor drifts by 2%, your filter shape changes noticeably.
It could even go unstable.
Right. But in a passive LC ladder, you could change a component by 2, maybe even 5%, and the filter shape basically shrugs. It barely moves.
It's rock solid. Why? What's the physics protecting it?
It all comes down to how they handle unwanted energy. A resistor just burns energy as heat. An active circuit tries to control it with voltage. But an LC ladder, it reflects energy. It works like a mirror.
The mirror?
Yes. If a frequency isn't supposed to pass, the ladder doesn't absorb it and burn it. It physically bounces it back to the source. That property, that losslessness, makes the whole thing incredibly resilient. Maximum power only gets through at the frequencies we want. Everything else is rejected, not destroyed.
So they are perfect, stable, robust, no power required.
They would be perfect, except for one massive fatal flaw.
The inductor.
The inductor. Coils of copper wire wrapped around magnetic cores. They're bulky, they're heavy, they pick up magnetic interference. But the real nail in the coffin, you cannot put an inductor on a silicon chip.
Right. You can make a transistor a few nanometers wide, but you can't make a microscopic copper coil that actually works right.
Exactly. The physics just doesn't scale down. And modern electronics is all about integrated circuits. If you can't print it on a chip, you can't really use it. So engineers in the 70s had this crisis.
Okay.
We wanted the mathematical robustness of the massive LC ladder, but we needed it to fit on a microchip.
An impossible contradiction. You want the physics of heavy machinery, but the form factor of a microchip. And this brings us to the grand synthesis, the solution, the leapfrog topology.
This is one of the most intellectually satisfying ideas in all of engineering. The leapfrog filter is an active circuit. It uses op-amps, resistors, capacitors, no inductors anywhere. But it doesn't use the Sallen-Key design logic.
So what does it do instead?
It simulates the physics of the LC ladder.
Wait, when you say simulates, we aren't talking about software here. This is still analog hardware.
Correct. We look at the actual differential equations that govern the currents and voltages inside that big, heavy LC ladder. The math that says current flows from inductor A to capacitor B.
Okay.
And then we build a circuit using op amps that solves those exact same equations.
So we replace the physical components with their mathematical equivalents.
Precisely. In the leapfrog topology, we use active integrators, which are just op amps with capacitors to pretend to be the inductors and capacitors from the ladder. And then this is the key. We simulate the connections between them using feedback loops.
And that's why it's called leapfrog.
Right. If you look at the diagram, the feedback loops literally jump over adjacent stages. Stage 1 connects to 3. Stage 2 connects to 4. They're playing leapfrog.
And what's the result? Do we actually get that robustness back?
Right.
Or is it just a cheap imitation?
We get it back. That's the magic. Because we are simulating the internal structure of the ladder, this active circuit inherits the low sensitivity of the passive one. Even though it's made of sensitive op amps, if the components drift, the filter stays stable.
That is incredibly cool. It's like
Yeah.
we couldn't shrink the copper coil, so we built a mathematical ghost of the coil using silicon, and it works just as well.
That's the grand synthesis. It bridges the gap. You get the compactness of modern chips with the rock-solid physics of the old-school heavy machinery.
It really does circle back to where we started. This idea that we're just building machines to do math.
It does. We went from the passive era, where the physics of the components was the math, to the active era, where we used op amps to force the math. And then finally, with leapfrog, we used the active components to simulate the passive physics.
A full circle. So let's wrap this up. We've covered a ton of ground. If you listening are going to take away one single model from this deep dive, what should it be?
I think it's the concept of trade-offs. We saw it everywhere, right? The passive ladder. Great robustness, but it's huge. The Sallen key. Small and powerful, but push that gain too hard and it can get unstable.
The Chebyshev.
Yeah.
You get that fast roll-off, but you have to pay for it with Ripple.
And finally, leapfrog. It's complex to design, but you get the best of both worlds.
So design isn't about finding the perfect solution. It's about choosing which problem you're willing to live with.
Exactly. You trade power for game, you trade ripple for speed, you trade complexity for robustness. At the end of the day, there is no free lunch in physics.
And whether you're using a heavy copper coil or a microscopic op amp, the goal is always the same.
To use the language of mathematics to shape the physical flow of electrons, you're telling the signal what it's allowed to be.
I think that's something for everyone to think about next time they put on noise-canceling headphones. There's just a ton of algebra happening in there to keep the world sounding crisp.
It's an art form. It really is.
Go shape the signal. That's the final thought from the text, and I think it's a good place to leave it. Thanks for helping us decode all of this today.
My pleasure.
And to you listening, thanks for diving deep with us. We'll catch you on the next one.